So section 4.2, regarding something called a logarithmic function, may very well be the most confusing section in the entire chapter or perhaps semester. Only because it deals with something just different in ways and kind of difficult to necessarily describe what's happening other than just kind of comparing it to something we've just learned about. So we've learned about the exponential function back in 4.1, and we saw the pattern, simple table of values for this specific function of 2 to the x, and we saw that it would be this increasing function going through the point 0, 1, we're going to say that's 0, 1, asymptoting at the x-axis, or y equals 0, and have that general shape. So now let's bring back the idea of inverses that we saw much earlier in the semester, and ask, what would the inverse of this function be? Well, it would be the swapping of x and y, so you'd have this table of values right there, and you'd end up with a graph that looks like this. So it's still increasing, but now notice the reflection across this y equals x line has it with a vertical asymptote, so it's asymptoting along the y-axis now. It is still increasing, but it increases at a much slower rate, right? Exponential increased at a faster and faster rate. It increased at an increasing rate. This is increasing, but at a decreasing rate. It's slowing down. Now, it's never going to turn and decrease. It's never going to go downward. It's just going to go slower and slower in the increasing pattern off to the right. But this function, this graph here, it is a function. And so we want notation to describe it. So the notation used to describe the function with this pattern, or in other words, the inverse of an exponential, is something we call a logarithmic function. Now, logarithmic, we're going to shorten the logarithm to log, L-O-G, and you're going to see that L-O-G used to describe this function. So we have the log. Now this little number you're going to see down below here, the subscript, this is what we call the base of the log. So this is log base b of x. X is like the input now. Arguably, you could even have parentheses around it as it's the input into the logarithm, okay? So we're saying that this function is y equals this notation. Again, new notation to us. But what this is really telling us is the same thing as creating this what we call exponential form. So the really interesting, and again, kind of tricky thing, this logarithm, what this really represents, it is the number, right, y. It represents the the number that would need to be the exponent of this base b to get this value x. So log base b of x is y, if and only if y is the exponent on the base b that gets you x. Again, that right there can be very confusing, the correlation or the relationship between those two statements. Basically, those two statements say the exact same thing. If I tell you this, you have this. Or if we see this, we have this. So that's the first thing we want to understand is how to go between them, because there are certain situations where one is definitely easier to work with than the other. So first thing we learn is how to write in each form and the other form. And so to do this, what I like relying on, especially when going from the logarithmic to the exponential, it's a little easier this way, is something I call the cycle. And so again, when you're in this form, y equals log base b of x, we know that this represents this. So the cycle I'm referring to is if you start with the base, b, and you think of b raised to the y equals x. You'll get b raised to the y equals x. Start with the base, wrap around like that, you can convert it into that form. Now, in this very first example, what we're saying, when we see log base 2 of 8, again, I don't expect anyone to know what that stands for right now. They're telling us it's equal to 3. It's equal to apparently a nice convenient number. But what we can see is that this is saying the same thing as 3 is the exponent on 2 that gives us 8, right? That's what this was telling us. But here's the cycle helping us. Use the cycle, and we've got base 2 to the third equals 8. And as soon as I write that, we say, well, yeah, 2 cubed is 8. That makes sense. This is the exponential form of the exact same information as this logarithmic form. That's what we're doing here. Two different things that say the same thing. They just look very different. So we'll do that same approach for the next three. Now, one thing that's important here, and we'll talk more about it later on, is that when we see just log, meaning you do not see a base down here, we will actually find out that that is a base of 10. That's the standard base for a log. Any other base will have to see the value. But in this case, we just have the value 10. And so we can use our cycle again, and this says 10 to the first equals 10. That makes sense too, right? 10, anything to the first power is that value, so that works. ln, this is something else we'll see. I think it's on the next page even. The idea that ln is a logarithm. It actually stands for the natural log. ln represents the log with that base of e that we saw in the last section. So e, Euler's number, the natural base, e. So if you have a log base that specific number, that happens a lot where we actually give it its own notation and called it ln. And now, if we use our cycle is telling us that e to the 0 equals 1, which definitely makes sense because anything to the 0 is 1. And we'll actually come back to that idea as well later on. And the last one here, we've got log base 3 of 1/9 is -2. So start with the base and say 3 to the -2 equals 1/9. Now, going the other way, really, I still like to use the cycle. Other people have other ways to think about where these numbers go, but I imagine almost like if you're going to fill in the cycle, fill it in with those numbers. We know we've got log base, okay, well the base is 10. Now to the, so the thing that goes on the other side of the equal sign is supposed to be the 3, and then equals the thing you get on the other side of the equal sign, 1,000. So again, I'm using the cycle, but in reverse, where I see, as I read this, I follow through the cycle. 10 to the third equals 1,000. And that gets me back to the logarithmic form, log base 10 of 1,000 equals 3. Again, this takes some time, takes some practice. You can, even if nothing else, write it out and then double check it. Check it with a cycle. 10 to the third equals 1,000. Yep, that checks. Same thing here. I'll start with a log. You can always start with your base. Whatever your base of your exponent is the base of your logarithm. But then it should be to the, so on the other side of the negative sign, or equal sign, should be the exponent of -1 equals, bring the cycle around, so the 1/2 is inside there. Log base 2 of 1/2 equals -1. 2 to the -1/2 equals 1/2. There it is. Last two. I'll go ahead and start with saying log base e, and then we'll change that here in a second. E, using the cycle, to the 2 equals 7.389. Now I will use a approximation here because we're just throwing a decimal in. And so now I will rewrite log base e as we mentioned above. Log base e will be ln. So ln of 7.389 is approximately 2. Last one, base of 9. So log base 9. 9 to the, okay, so on this side of the equal sign goes the 3/2 equals 27. 9 to the 3/2 equals 27, and done.